going to present to you nothing less than the origins of the universe, subatomic particles, and the world's largest science project ever. I want to explain the Higgs field, an incredibly important force that governs our universe. To talk about the Higgs, I have to start by going back to the basics. To understand the origins of the universe, we have to understand what it's made of. Atoms, right? Everything in the entire universe is built of atoms. We also know that atoms are made up of even smaller particles, protons and neutrons and electrons. And we found out that there are even tinier particles after that, called quarks and leptons. So with this knowledge, we feel pretty confident that we can explain most of how the universe works. The Standard Model is the term used to describe our current understanding of how all the known parts of the universe fit together. It combines all the subatomic particles and most of the forces into one theory and basically describes how they all interact. But scientists realized that there was still a piece missing in this Standard Model explanation. They didn't know why all these different particles existed. What happened in the beginning of time to make all these particles come to exist? What made them different from each other? Why do some particles have mass and others have none? Simple, it's because of the Higgs field. Let's back up a little. We know that immediately after the Big Bang, the universe is infinitely hot, dense, and perfectly symmetrical. That is, every part of the universe was exactly the same as everywhere else, and everything was moving at the speed of light. But it only stayed that way for about 10 to the negative 10th seconds. So what happened that changed this? Well, in the 1960s, some brilliant physicists theorized that less than a second after the Big Bang, an invisible force came into play that affects literally everything in the universe. Without this force, there'd be no atoms, no molecules, no stars, no galaxies, and no us. We call it the Higgs field after Peter Higgs, one of the physicists who came up with this theory. The Higgs field is what caused all these perfectly symmetrical particles to take on mass after the Big Bang. Before that, there was no mass, and without mass, there was nothing to distinguish all these particles one from another. So what is a field, really? It's invisible, yet it affects everything. It's not a physical thing we can touch, but it's present everywhere in time and space. Things can be, and are, affected by these invisible forces. Let's compare the Higgs field to the magnetic field. That's one we're all familiar with, right? The magnetic field has different effects on different materials. Some don't interact strongly with the field, and others do. Similar to the magnetic field, the Higgs field interacts with some particles strongly and some not at all. The more a particle interacts with the Higgs field, the more mass it has. That's how we have quarks and leptons and electrons, because each of them interact differently with the Higgs field. So here we have this theory, this idea of how all the elementary particles in the universe came to be so diverse. But until a relatively short time ago, the Higgs field wasn't proven to exist. Peter Higgs had suggested that you could find evidence of this field in a certain particle of energy called the Higgs boson. Scientists at the Center for European Nuclear Research, or CERN, decided to carry out the biggest science project the world had ever seen to test this theory. They built the largest scientific device in history, a machine called the Large Hadron Collider. It's a circular tunnel over 300 feet underground and 27 kilometers around, with building-sized collision centers along the way. This machine was designed to accelerate protons around the ring until they were speeding along at nearly the speed of light, and then smash them together to simulate the Big Bang. These protons were smashed together so energetically that it created a disturbance in the Higgs field. The theory was that if they could create a big enough disturbance, so much energy would be thrown around in the collision that the theorized Higgs boson would come into existence. The Higgs boson is an excitation of the Higgs field, or what physicists call an energy particle. Compare the Higgs field to a lake. Creating a disturbance in the Higgs field is like throwing a rock into a completely still lake. The harder you throw the rock in, the bigger the ripples are and the easier they are to detect. Similarly, if you smash particles together with enough energy, you'll create ripples in the Higgs field big enough to be detected. The Higgs wave is a ripple in the Higgs field, and a Higgs boson is the smallest possible ripple, or the one with least intensity. In order to create this smallest possible wave, you have to make a giant disturbance in the field. But what scientists at CERN soon found out is that just as ripples in a pond quickly die away, Higgs bosons also decay quickly. In fact, they decay at such a fast rate that it is impossible to study the Higgs boson itself. Instead, you have to search for and study the other particles that the Higgs decays into. Scientists were able to predict in what way the Higgs boson should decay, so they knew what to look for. After running many experiments and sifting through the masses of data they collected, scientists at CERN were able to confirm that they had found a new particle with the correct mass of around 126 giga-electron volts, the Higgs boson. The Higgs boson isn't so important in itself, it's what it tells us about the Higgs field that really matters. Finding evidence of the Higgs field has been a huge breakthrough in science. Without the Higgs field, particles wouldn't be able to settle down into atoms and molecules and stars and galaxies. The Higgs field is what broke the original symmetry of the universe by causing particles to take on mass, allowing life to eventually form. The huge role that Higgs plays in our existence makes it an essential part of our scientific